Hello and welcome to the second mock AMC video. This will be the one for the AMC12 paper. If you are taking the AMC10 and you haven't already, I would love if you would check out the AMC10 video, which I've uploaded a few days ago. It has a different set of questions. There's no overlap, even though the actual AMC10A and 12A will have overlap and the actual 10B and 12B will have overlap. There's no overlap here. So you can try this set of questions completely independent of the mock AMC10 paper, which I've gone over in the other video. Now, in the interest of time, I'm not going to be going through the format of the AMC12 because it's the same as the AMC10. And if you are taking the AMC12, there's a fairly high chance you have also taken the AMC10 before. So I guess it suffices to say that in recent times, the cutoff score for the AIME would be somewhere in the range of about 90 or maybe a bit less if it's difficult and a bit more if the paper is easy. So I don't want to be held to that because it depends also on what the MAA decides in terms of the number of qualifiers they would accept for the AIME, and that does change from year to year. But I'm just going to get straight into the problems. It is a 75-minute test, but I'm not going to be able to go through it in 75 minutes. I'm going to try to go over the questions in about 90 minutes or so from this moment. So before I go through the questions, if you haven't tried it yet and you would like to give yourself a final mock paper before the AMC, be it the 12A in a few days or the 12B in slightly over a week, feel free to pause this video, try the questions, and then come back here to see how you did. Now, before I go through it, just a bit of a disclaimer. Some of you may feel that this paper is not actually that much more difficult than the AMC10. That's actually something that does happen nowadays, once in a while. Right? It does happen that the AMC10 and 12 difficulties are oddly quite close to each other, except that the AMC12 involves some further advanced topics. So if you feel that way, to be fair, that is somewhat intended. On the other hand, if you find that this is really difficult, that's entirely possible. It is remarkably difficult to benchmark one's own questions and figure out how hard it would be for someone else to think of the same thing as you. But anyway, this is the last chance you have to pause the video. If not, in a few seconds, we shall begin going through the problems. Alright, here we go. Now, the first 10 questions, we should go through it very quickly. In terms of this video and also in terms of the actual AMC12, if you are taking this AMC in the attempt to qualify for the AIME or better, you would definitely want to be done with the first 10 questions in about 20 minutes or 25 minutes at most. Okay, so question 1 is a calculation problem. Don't mess it up. It is going to be just 2 to the power of 0 and then 2 to the power of 2 to the 0, which is 2 to the 1. And that should be all. Nothing complicated here. Question 2. Let x be a real number. Which of the following can never be larger than all the other 4 options? Now, this is something that the AMC is able to ask because of the multiple choice format. They can ask you something like which of these cannot be true, which of these must be true, which of these could possibly be true, and so on. You can try substituting in different values, but the key thing that we would actually be able to do is just to say that negative x squared is always going to be less than or equal to 0. And there is an option here which is 2. So we know that 2 is always bigger than negative x squared, so negative x squared can never be bigger than everything else. If you were to check very carefully, there are values that would make A, B, C, or D the largest out of these 5, but never the last one. Question 3. 9 consecutive integers are summed. Which of the following is a possible result? You can solve this as an algebra problem, letting it be x, x plus 1, x plus 2, and so on. But the key thing is that the sum of 9 consecutive integers is just 9 times the median of your 9 consecutive integers, and the median is the middle number. So all we need to do is look at these options, find out which one of them is a multiple of 9, and then that would be possible. The way to test for multiples of 9 is to use the divisibility test, which is adding up the digits. So the digit sum, 3 plus 4 plus 5 is 12, and then each time it just goes up by 3. So out of all of these, the only one that is a multiple of 9 is option C, because its digit sum is 18. That is also a multiple of 9. For question 4, the distance between two distinct vertices of a cube is square root 6. What is the product of all possible volumes of the cube? So the thing that will affect your answer is which two vertices are square root 6 apart. And if we were to draw a cube out, drawing is not too good, but I think it will do for now. Right, the first possibility is that these two are square root 6 apart. So your side length, I'll call that x, can be square root 6. The second possibility is that the two vertices are on the same face but not on the same edge. So that means that they are separated by a diagonal like this. And if this is x and x, the diagonal would be square root 2x. So this would give you x equals to square root of 3. The last possibility is that they are not even on the same face at all. And by not on the same face, by not on the same face, the only way that you can have vertices not on the same face is that they are on the long diagonal apart. Now, in order to get the distance of the long diagonal, this long diagonal by Pythagoras or a distance formula would be square root of x squared plus x squared plus x squared, which is going to be square root of 3 times of x. And so x would be square root of 2. Now we want the product of all possible volumes of the cube. That would be the first one cubed times the second one cubed times the third one cubed. It is easier to multiply them together first, because if you realize square root 3 times square root 2 is square root 6, and square root 6 times square root 6 is just 6. So your answer would be 6 cubed, and that is 216. For question 5, this is yet another problem where you can just use simple algebra to write x in terms of y and z, do some substitutions, and eventually solve for z in terms of x plus y. Or rather, solve for x and y in terms of z. But it's a lot easier if we actually notice that all these 3 fractions are essentially just comparing how x, y, z is going to be partitioned if you separate x from y and z, y from x and z, and z from x and y. So the easiest way to do it would be to do something like let x plus y plus z equals to, let's say, a. Now, the first fraction, x over y plus z is 1:3, tells you that x takes 1/4 of a, and y plus z takes 3/4 of a. The second one tells you that y to x plus z is 1:4, so y takes 1/5 of a. And so z would take the rest. Oops, forgot the a. So z is 11 over 20a, and then z over x plus y is equal to 11 over 20 over a fourth plus a fifth, which is 11 over 9. Right? And then 1 over k is equal to 11 over 9, so k is 9 over 11. Question 6. What is the sum of all possible values of m such that x squared plus mx plus 2022 equals to 0 has 2 positive integer solutions? Now what we don't want to do is to substitute in different possible values and try to see what it could be. Instead, what we would like to do is to use Vieta's formulas. And for Vieta's formulas, the 2 positive integer solutions can just be called alpha and beta. and alpha plus beta would be negative m. Alpha times beta would be 2022. Now, pro tip, it is a good idea to know the factorization of whatever year you are taking any competition in, as well as possibly the years that are adjacent to it. So 2021, last year, is 43 times 47. 2022, which is this year, if you're watching the video in 2022, is 2 times 3 times 337. And next year, 2023, is 7 times 17 squared. 7 times 289. So it's good to know this in the likely event that at some point you need to know the factorization and you don't want to waste a few valuable minutes checking if 337 is prime. So now that we have that down, since alpha and beta are positive integers, the only possibilities for your alpha and beta are that it is 1 and 2022, 2 and 1011, 3 and 674, and then 6 and 337. So m would be negative of the sum. So if we just add these up and put a negative in front, we will get the 4 different possible values of m. And if you add these carefully, it is not too difficult to see that it is option A, negative 4056. Now, quick little tip for when it comes to these sorts of additions, if you're pretty sure you're correct for an early question, usually you don't have to really do the addition, right? Just estimate it, 2000, 1000, 1000. So this thing should be about negative 4000. And then look at the last digit, 3 plus 3 plus 7 plus 3, the last digit should be 6. So you get to save a little bit of time on calculation. And that can be very, very valuable in something as time-pressed as the AMC. Question 7. 2 distinct numbers are selected uniformly at random from the set 1 to 12. What is the probability that their difference is a divisor of the larger number? This is a very boring but standard probability question. How I will try to make it a little bit more efficient is to call it not x and y. I'll call my 2 numbers, let's say a and a plus d, d for difference. And so what I want is d divides the larger number. And d divides a plus d is the same as d divides a. So all I need to do is just to write down different possibilities for d and see how many different possibilities there are for a, which do not exceed 1 to 12. Now we know that there are 12 squared different possibilities normally, but this is distinct, so it's actually 12 choose 2. Right? So we just need to count how many there are. If d is 1, a could be anything from 1 to 11, not 12, because a plus d is at most 12. If d is 2, we go from 2 to 10. If d is 3, we go 3, 6, 9. If d is 4, we have 4 and 8. D is 5, we have just got 5. And if d is 6, we have only got 6. So I can just count how many there are down here. 11, 5, 3, 2, 1, 1. And I get 23 of them. I'm pretty sure at this point that it should be 23 over 66, but let's just double check that 12 choose 2 is indeed 66, which it is. So therefore my probability is 23 over 66. Question 8. 1st January 2023 falls on a Sunday. On what day of the week does 1st December 2099 fall? Perhaps some of you may be a little annoyed by this question because it seems to require a little bit of general knowledge, like you need to remember there are leap years. You need to remember that December has 31 days. But I think the AMC tends to do this once in a while. So I wanted to make an attempt to imitate the AMC format, and that includes making some assumptions of your knowledge which you may protest are not really well known. I don't know whether you would consider it to be well known, but I think the leap years being on multiples of 4 and December being 31 days is still reasonable. I did not expect you to know the number of days of every month in the year. So how do we get from 1st January to 2023 to 1st December 2099? My strategy is to go and fast forward to 1st January 2100, where the prospects of anyone watching this video being alive is potentially not that high. Then we will go backwards 1 month. So this is 77 years. This is 31 days. So for 77 years, we know that there are actually going to be 77 sets of 365 days. So that doesn't change the day of the week. But there are leap years, and the number of leap years will tell you how many extra days there were. So in this period, my leap years would be, and I'm just writing the last 2 digits because that's the test for 4. The leap years would be the ones from 2024 all the way to 2096. And the number of them, 96 minus 24 divided by 4 plus 1 is 19. So you have basically gone forward 19 days, 19 extra days. So you've gone forward 19 days, but you went backwards 31 days. So the net effect is just going backwards 12 days. And going backwards 12 days is the same as going forward 2 days, and so therefore the answer is Tuesday. Okay, here I'm cheating a little bit because I said these questions, so I'm trying to give the absolute most efficient way to do it. To be fair, for the AMC, if you would be trying to finish all of it in anything close to 75 minutes, you would have to be doing almost every question in the most efficient way. It is not likely that you would do every question in the most efficient way, but that's okay. If your target is, let's say, something like 17 or 18 questions with room for a couple of mistakes, then most certainly you don't need to be pressing to this extent of getting the most efficient solution every time. But it's good to have efficient solutions. We get ourselves more time to think of the fun and also more difficult questions behind. Question 9. The figure below, triangle ABC and triangle CDE are congruent isosceles triangles where AB equals to AC equals to CD equals to DE. Extend DE to intersect AB at F. If AE equals to 7 and EF equals to 5, what is the length of BC? Now, congruent isosceles triangles is a massive amount of information. We have 4 equal angles in addition to the 4 equal lengths that are given to us. We are given these 4 equal lengths. But the equal angles is pretty helpful because among all of these, we get one set of parallel lines. So the one set of parallel lines tells me that this 7 to 5 is actually going to be similar to both of my congruent isosceles triangles, so everything is in the ratio 7:5. The only thing left for me to do is to find some meaningful equation to write down so that I don't get too messed up and end up doing more calculations than I would like. So you need to decide, how am I going to get to BC as efficiently as possible? And if let's say that you are not too sure, I suppose one quick way to do it would be to just let this length be 7x and this length be 5x and see what else we can do with them. And the nice thing here is that you actually realize that this length here is also equal to 5x because it's on the other triangle, and so 5x plus 7 equals to 7x, and x is 7/2, so BC is 35/2. Question 10. Yeah, this is another question that can only be really asked in the AMC because of the multiple choice format. Right. Here's a graph. Which of these could be fx? And I've mentioned in the question that the length of one small square in these directions may not be equal, so don't take it to be to scale, just take the general shape. Right, so it is a shape, but whether I've stretched it out in order to make it look like this, that is completely something that you cannot assume. Right? Is this really to scale or is this not to scale? Now, just because I have potentially stretched it out, it does not really mean that the features can change. The only things that can change would be, let's say, the scale of it. And we don't know where the x and y axes are. But we do know that, firstly, it is going to be tending towards infinity in both directions. We can make that reasonable assumption that there is not going to be some mystery turn down here which are not shown. That wouldn't really make too much sense. So therefore, it already tells you that the degree must be even. The other feature is down here, and the feature down there is just that it is not symmetric, which turns out to be enough information. It's an even degree, so the first two are out since they are degree 3. We also have C and E being actually symmetric expressions. Right? So this would be symmetric about x equals to 1.5, and option E would be symmetric over x equals to 2.5. Right, we can see that because the roots are basically going to be symmetric, and if the roots are symmetric, then the whole function would also be symmetric, the whole polynomial. Right, and so therefore the only possible option is D, and it sort of makes sense. Right? X minus 1 squared, so it makes sense that your 1 is actually down here, and then that is your 0.10. Right? So this is actually 2, 0, and this is 3, 0, although that is not part of the required solving in the question. And we're done with 10 questions in about 20 minutes, as I have suggested, so this is great. Let us continue. Question 11. This is not a difficult question, it just has a slight tongue-in-cheek nature of it, but once you have spent a few moments to process what it's asking, it's actually a pretty easy question. The Bank of Massive Binariness has decided to issue coins valued at log base 2 of A, log base 2 of B, and log base 2 of C dollars, where A, B, C are positive integers. It is possible to use a combination of Bohm's coins to make exactly both log 2101 and log 21111 dollars what is the smallest possible value of A plus B plus C. This has nothing to do with binary. It doesn't even have anything to do with the base 2. The only thing that you actually need to understand is that a combination of logarithms basically is just multiplying together the insides. So it just means that you can combine your ABC via multiplication to get both 1001 and 1111. Now, 1001 is 7 times 11 times 13, yet another go-to factorization that you would hopefully be familiar with. 1111 is just 11 times 101, is 1111. So we can see that immediately, the only thing that these prime factorizations have in common is the 11. So that means two things, right? First, it is very logical that you would like to have a coin of denomination 11. And secondly, it also means that it is very logical that you cannot combine 11 with something else. Otherwise, if you combine, let's say, 7 and 11, that would be useless for the 1111 combination. So your coins, by this reasoning, would just be 11. And once you have settled 11, you only have 2 coins left. You have to use the other 2 combinations. So 11, 91, and 101 gives us 203 as the most optimal combination. Question 12. In the figure below, a parallelogram is divided into 8 regions using 4 straight lines. The areas of 3 of the regions are 20, 22, 1, 1, 1, 1, and 99 respectively as shown in the figure. What is the area of the shaded region? To be fair, this question is not the most original question, and I think also that the AMC does also not always have the most original questions throughout, right? There will tend to be a couple of them which are sort of repeated from old AMCs or from other contests. So I decided to include one that I know has been asked in a few different contexts before. It's actually pretty difficult if you have never seen the idea before, but if you have seen the idea before, you immediately know what to do, which is that we don't have enough information to find any lengths or heights or widths or whatever else you might conceive. We also do not have any nicely placed similar triangles. So the only thing that we can do is to work with area, and we will use 2 different combinations of area which equate to half the parallelogram. The first combination is here. This red region would equate to half the parallelogram, and that's also involving all the given areas. The second portion that involves half the parallelogram is this portion over here, which involves the shaded area. And if we cancel off the overlapping portion between the red and the yellow regions, we see that we get the rather simple conclusion that the shaded area is the sum of those 3 regions. And that is about it. So it's a simple idea if you have seen it before. Take note of this whenever you are given some area problems. You can equate areas even if you don't know what they are. Question 13. After filling a 3 by 3 square with each of the numbers 1 to 9, we say that the result is a slightly magical square if the numbers in each of the rows and columns sum to 15. How many slightly magical squares are there? Rotations and reflections are considered to be different, which sort of makes sense if you look at how big the options are. It's hard to imagine that there are, 432 different squares without including rotations and reflections that are semi-magic squares. So it's not very surprising that we have to account for that. Now take note also that when we have this slightly magical square, this is not a magic square. The full magic square would also include the diagonal summing to 15, which is why our options here are a fair bit bigger than what we would encounter in that case. So, if you aren't so familiar with the original magic square, this question would kind of be halfway through the full magic square. If you are familiar with the full magic square, you don't really want to use it, to be honest, because if we use the full magic square information, it is not very clear what sort of loosening we can do in order to get all the slightly magical squares. So let's try to solve this as a mini puzzle, right? Let's just try to find one way to do this without consulting our magic square. Now, whenever I'm doing a puzzle, I like to think of what's the biggest nuisance. The biggest nuisance is the thing that is the most difficult to make consistent with the other conditions in the question. And I think here, as is often the case, either the smallest number, which is 1, or the largest number, which is 9, would be your nuisance. Because there aren't that many combinations that would get them to 15, whereas if you used 5, let's say, there are lots of combinations that gets it to 15. So let's try 9. Let's imagine we put 9 in the middle. Now, we need to have 6 more to get it to 15 in both the row and the column. From my remaining numbers, the only way that you can get to 15, in other words, getting those 2 to 6, would be 1 and 5 or 2 and 4. Now, since I'm allowing rotations and reflections, I have no reason to believe that the position actually matters too much. I'm just going to put them in some random order like this. Okay, and then the numbers that I'm left with are 3, 6, 7, and 8. Now you can see that 3 is very far removed from 6, 7, and 8, relatively speaking, and it is also very small. I cannot put 3 and 1 in the same row, otherwise I know that the other number needs to be 11, that's too big. I also cannot put 3 and 2 in the same column, otherwise it will need to sum to 15, the other number will be 10, which is also not possible. So the only place that 3 could go is away from the 1 and 2. And that will fix the 7, the 8, and the 6. Everything got fixed. So this already tells you how this is going to go. Firstly, you place the 9. And there are 9 locations to place the 9. Secondly, you will place the 1 and 5. For the 1 and 5, you basically can choose row or column and you can sort them around. So there are 4 ways to place the 1 and 5. Then with the 2 and 4. The 2 and 4 will go into the remaining row or column. They can still swap around, so there are 2 ways. And then after that, your 3, 6, 7, 8 are fixed. 3 would avoid the 1 and 2, and once you avoid it, then you will end up with 3, 4, 8, 8, 1, 6, 6, 2, 7, 7, 5, 3, regardless of where the 9 was placed and the 1, 5, and 2, 4 were placed. Now, if you're not fully convinced, try putting the 9 somewhere else. You will see that there's always going to be 1 and 5 and 2 and 4, which are going to be fixing the location of 3 and then accepting the locations of 6, 7, and 8. So therefore, the only ways that we can do it would be from here. 9 times 2 times 2 times 2 is equal to 72 ways, which is option C. Okay. Question 14. 2 posts situated 6 yards apart are connected by an inelastic 10-yard rope. A dog's leash is attached to the rope. What is the area of the region which the dog can reach? Now there's something interesting about this question, which is that maybe if you are watching this from the United States, you don't think that there's a big deal here. But if watching this from Singapore, you will be slightly bewildered. And the reason is not because of the use of yards. The reason is just because this is basically a question that is defining an ellipse. And coding sections are very much a part of the Algebra 2 or pre-calculus curriculum in the United States. So you probably think this is really easy. For a Singaporean audience, that is not true, because this does not come into our curriculum until a pretty late stage. So there are lots of differences in curriculums and in syllabi. Is that plural of syllabus? Syllabi? I think so. The syllabi in different countries. So let me just explain the definition of an ellipse for those of you who do not know the definition of an ellipse. An ellipse is not just defined as one elongated circle. Right? An ellipse basically is defined using 2 points which are called the foci. I'll label them F1 and F2. So the ellipse is actually a set of points. Let's call it P, such that PF1 plus PF2 is some constant K. Right? And the K is kind of like analogous to the radius, but not really. It's maybe a bit more analogous to the diameter if you think about it. Okay, so K is kind of analogous to the diameter. In our case, the distance between the foci is 6 and the K is 10, because the rope is inelastic, means that wherever the dog goes, the sum of the straight line distances is at most 10, because that's as far as the rope is going to go. It is 10 yards in total. It can of course go inside, and inside will be when the sum of distances is less than 10. The rope can be a bit slack as well. It does not really need to be a straight line. So therefore, all we need to do is to find the information about the ellipse. I'll draw in the center of the ellipse. Distance here is 3 and 3. You would like the fixed sum to be 10, so we can just use these 2 points to get our information, if you don't remember the formula for the semi-major and semi-minor axis. Right. I need this plus this to be equal to 10. So it's pretty easy to see that this plus this is actually equal to this entire length. That length is 10. And so therefore, the distance will be 5 on each side. So I can label a 2 and a 2. It's also pretty easy to see that if I want to get this distance here by symmetry, it should be 5 and 5. So Pythagoras gives me that this length is 4. And so therefore, the area of an ellipse is equal to pi AB, where A and B are kind of the analogs to radius, right? The semi-major and semi-minor axes here, 4 and 5. So your area is pi times 4 times 5, which is 20 pi. Okay, so far so good, I think. We have gotten to 14 questions in about slightly over 30 minutes of discussion. Okay, question 15. 3D geometry is not usually easy to visualize, and I know there are some of you who are very, very averse to it. But the good news here is that for a question like this, you don't really need to know that much. You only really need to focus on one portion at a time. Now, my suggested solution here would actually be to use volume. The question is asking for volume of the spheres, but I'm not really drawing the spheres. I'm using volume to relate the radii. So let's just suppose that the radii are R1 and R2 respectively. Now, I think I will just draw a rough octahedron. Now this is the top half and this is the bottom half. Gosh, that looks horrible. But the reason why this looks very horrible is that that's about the quality of the image you need in your mind. It doesn't need to be really good. This looks atrocious. You don't really need a very good quality image. You just need to be able to focus on one portion at a time. So the first portion is that I want to think of the volume in terms of two big square pyramids. The top half and the bottom half. So two pyramids, the area of the pyramids is 1/3 times base area. I'll let the length be 1, so it's just times 1 times the height. Now the height is actually going to be R2. It's the distance from the center to the top, so that's R2. Now at the same time, I can also think of my volume in a different way. I can think of my volume if let's say that I'll just focus on the top half for now. This could be the center. Now R1, which is the in radius, it's just the distance from the center of the square face here, the square cross section here, to the centroid of the equilateral triangle. And that is going to be the foot of the perpendicular by symmetry. That is R1. So I don't actually need to calculate anything. I can just say that if I were to split it like this, I've just gotten myself a pyramid. And there would be 4 such pyramids corresponding to each of my 4 triangular faces. So I end up with 4 triangular pyramids on each half. Each triangular pyramid has base area of one of those equilateral triangles, which is root 3 over 4. And the height is R1. So you can solve and get R2 equals to square root 3 times R1, and the ratio of volumes of the spheres is just going to be the cube of that. So your answer is 3 root 3. Okay, next up, question 16. How many values of x in the range 0 to 360 degrees satisfy this equation? And this is the point where we are at the last 10 questions and we also need a bit more space. I am going to give myself a bit more space. Now, what you will need to use for these questions would actually be the trigonometric sum to product identities. Right? And that is in order to exploit the fact that we have pretty nice symmetry going on over here. So we would like to use our sum to product identity for the sum of sines first. And so combining those which I have paired up, all of them are going to have the same sum of angles, which is 9x. And the A here is basically the average of these 2 angles. B here is half the difference. So the average is going to be the same if the sum is the same. And that's good news because I would like to take out a common factor and simplify this thing. So let's do that. Right, sine x plus sine 8x, you get 2 sine of the average, cosine of half the difference. And I have half the difference for, why did I put A? Sorry, that's x. I've got this for everything. And for the right hand side, you get the same factor, which is great news. You get half the difference, this time is 2.5x and 1.5x. If I were to now take that out, it means that I've got my first combination, and I can continue with the rest of this. And you see that I've got half as many expressions as I had at the start. There were 8, now there are 4, so I've definitely made some good progress. Now let's do it again using our cosine sum to product identities. So this would be 2 cosine A cosine B. And because once again, the average of these 2 angles will be 2x, so I can do it again. I get 2 cosine 2x sine, not sine, still cosine. 2 cosine 2x cosine 1.5x equals to 2 cosine 2x cosine 0.5x. So I get to take out one more possibility, which is cosine 2x equals to 0, or this last bit, which I'm going to move over, and rather humorously, I am going to use the sum to product identity a third time, although this time is cosine minus cosine. Right, this is the identity. There are 3 of these identities which we have used in the same problem. And this last one gives you finally a product of sine x sine half x equals to 0. So there we go. Right? We have got ourselves essentially 3 cases. Depends whether you want to further split the last one up. And we just need to count very carefully how many solutions there are. For sine 4.5x equals to 0, I'm going to use degrees because the question's in degrees and 4.5 is nicely dividing into 360. So for sine to be 0, the angle must be a multiple of 180. And so x should be a multiple of 40. And that gives you 0 to 320, which has 9 solutions already. Now, the next one is cosine 2x equals to 0. And for cosine 2x equals to 0, we know that this is 90 degrees plus 180n. It's lagging a bit, isn't it? Sorry about that. So yeah, I'm also cannibalizing all the degree signs. This is the AMC. We don't really have time to write everything so precisely. We shouldn't even need to have to write our working that carefully. So feel free to scribble, make a big mess as long as you don't read your own steps wrongly. Now, the last one, sine x and sine half x equals to 0 means that x is a multiple of 180 degrees or x is a multiple of 360. And if we look carefully, 0 is already there, but 180 is not yet there. So one more new value is 180. 0 has already been included, and 360 is not in the range. So we just have one more, and in total, 9 plus 4 plus 1 gives you a grand total of 14 solutions. Okay, question 17. Yeah, before 2006, the AMC12 was a lot easier. That's true for multiple reasons. And one of the reasons is that 2.5 marks were given for unanswered questions. And so getting to the 100 mark cutoff, as you might imagine, is not actually going to be very difficult. Right? It's also a little bit silly that you can just do 11 questions and just sit back and relax. You just do 11 questions and you leave 14 blank, and that would have given you 101 points. Just nice to guarantee getting into the AIME, which, 11 questions and then just check 11 questions really carefully is not exactly the best indicator of mathematical ability. So the AMC12 at that time had this scoring system. What the question here is asking you is that if we use that scoring system, how many scores would tell you uniquely the number of correct answers, wrong answers, and blanks that a student would have had for the AMC. Now I'm going to just make it a little bit easier for myself by multiplying everything by 2. So instead of 6, 2.5, and 0, I will scale it up to 12, 5, and 0 is still 0. Right, so that I work with integers, and this is not your chicken McNugget theorem, right? Because we are trying to ask for unique. We're not asking for can you express it, and also we have a fixed total of 25 questions. So this is a little bit different, or it's entirely different from your chicken McNugget theorem. Now, intuitively speaking, we would expect that the higher scores would be very much unique, and the lower scores would also be unique. So we just need to kind of see which is exactly going to be the cutoff point for us to get from unique to non-unique in both directions. Like, for example, a perfect score and 0 marks are both going to be unique. I'm going to split this into cases to help myself understand this a bit better. So I'll start off with the case where someone had no blanks. If the person had no blanks, the only things he could have gotten is multiples of 12, and he could have gotten all the multiples of 12 up to 25 times 12, which is 300. Remember, I'm multiplying by 2, you cannot actually get 300 points for the AMC. And there are 26 possibilities, all of which are 0 mod 12. Now, if I bring in one blank, it means that your minimum score is now 5. And the maximum score has dropped by 7 points. It is now 293. These are 25 possibilities, and these 25 possibilities do not overlap at all with the first 26 possibilities because they are all 5 modulo 12. And you can see that this will continue, right? The next time if I write 2 blanks, I'm going to get 24 possibilities, which are 10 mod 12. And so this will continue until I go through all the possible residues mod 12, because 5 and 12 are co-prime. It will not overlap. It will not be periodic any earlier than 12 steps, rather. Right? Because if it were, that means that I have got 5x is 0 mod 12 and x has to be 0 mod 12 itself. So it has to take 12 steps. So this goes all the way to 11 blank. And with 11 blank, you would have 15 possibilities from 0 to 14 correct answers. And after this, things are going to repeat. Because once I have 12 blank, things will repeat again here where I have got 0 mod 12. But I've only got 14 possibilities and the lowest score is 60. The highest score is 60 plus 13 times 12, which is 216. And that's not the important thing. The important thing is that this is a subset of what we had at the top. It's a subset of what we had at the top. And so if it's a subset of what we had at the top, we do know that it is definitely going to reduce. It is going to be subtracting away from my 26. So out of those 26, these 14 are not actually going to be unique. And you can see that this is the same thing that's going to happen throughout. The next ones will be 13, 12, and so on. And all of these are going to subtract away from the initial bunch. And when you repeat back the third cycle, that's just going to be repeating again. It doesn't really do anything different. So therefore, the combination that you get would be 26 minus 14 of the 0 mod 12, 25 minus 13 of the 5 mod 12, and so on. All of these are 12. So you get 12 unique values for each of the things modulo 12. And so therefore your answer is 12 times 12, which is 144. Many apologies for the lag. It seems that my computer also finds the AMC12 to be harder than the AMC10. Question 18. We have our sequences here. They are defined as follows, and they have this big gigantic recurrence. What you're asked to find is k, and k is basically how long does it take for both sequences to be periodic. So both sequences need to repeat. We know that it is not going to be enough for one value to repeat. And so if you try calculating some of the next few values, let's say that I just put in this is 0, this is half, this is 1, and this is minus root 3 over 2. Now A2 would be A1B0 plus A0B1. So that would be half again. And B2 would be B1B0 minus A1A0. That would be minus root 3 over 2 again. Now this is not enough, right? The answer is not k equals to 1 because I need the whole thing to repeat for 2 consecutive terms. So if we calculate this again, now it is not the same. Right? Because if we cross multiply it here, half minus root 3 over 2 and another half minus root 3 over 2, you get minus root 3 over 2, and then if we do the other one, you get 3/4 minus 1/4 is half. Seems to have swapped. It's not repeated yet, and if we were to continue, you would just end up with, let's say, 1/4 plus 3/4 is 1, and then this will be 0. So it has become 1, 0. I'm sure somehow you do find this a little familiar, don't you? You find this a little bit familiar? Because this is basically a bunch of trig values, right? 0, 1, half, and root 3 over 2 are your quintessential trigonometric stuff. And if these are your quintessential trigonometric stuff, you can ask why. And we can also pretty quickly answer why. We can answer why because our identity looks like the sine and cosine identities, where your an looks like sine and bn looks like cosine. So I'm going to do this substitution. And if we put this in, we get sine is sine times cosine plus cosine times sine. Cosine is cosine times cosine minus sine times sine. It basically tells us that what we are doing is nothing more than our Fibonacci sequence modulo 2 pi. Right? Because for sine and cosine, when we put the angle in, we would only be able to get it up to modulo 2 pi. So that's what we need. We just need to focus on the sequence of theta n underlying this. And for n equals to 0, the angle is 0. Sine is 0 and cosine is 1, that angle is 0. Sine of something is half and cosine of something is negative root 3 over 2 means that it is in the second quadrant, and the basic angle is pi over 6, 30 degrees. So this is 5 pi over 6. And we can see that this is how it's going to go, which is maybe not the most enticing way to go about this because it is very computationally intensive. But we realized that the 5 pi is kind of irrelevant. So I basically shall look at it like this. I want the period of this modulo 2 pi. Right? If I want the period modulo 2 pi, all I need to do, all I need to do is just to get rid of my fraction. So I'm going to divide by pi over 6. Scale it up, or rather scale it up by dividing by pi over 6. And at this point, I can just write it out, but I'm a bit hesitant to, just in case it really turns out to be 48 or 36. That might take a while. So to hasten things a little bit, remember we are still trying to make things go quickly, even though my laptop is actively trying to make me go more slowly. If we want to go more quickly, for calculation purposes, we can split this into mod 3 and mod 4. We know that in order to be recurring mod 12, just need to recur mod 3 and mod 4. And I'm sure it will repeat much more quickly mod 3 than mod 12, and same for mod 4. So we just write them down. Right, for mod 3, it starts off at 0, 2, 2. And then I just use my Fibonacci sequence mod 3. Right, just keep adding, won't take long. 1, 0, 1, 1, 2, 0 to n. Yeah, it's repeating. So it is repeating, and it took us 8 steps to repeat. Now, if we do it modulo 4, it basically start off with 0, 1, 1 because 5 is 1 mod 4. And this is faster, it only took 6 steps to repeat. So it takes 8 steps to repeat mod 3, it takes 6 steps to repeat modulo 4, so modulo 12, it would take us the lowest common multiple. It takes us 24 steps to repeat. And 24 steps to repeat would also guarantee that our original sequences repeat, so our answer is option C. Right, question 19. I'm going to probably need a page for some of these just to be able to write a bit more. So I'm going to space my questions out. By the way, just a reminder that for the AMC, which is going to be held online, you will not be able to draw the diagrams. You will need to draw a copy yourself. You will need to write anything from the question yourself. You can't just circle, underline, or do things in the question. So just take note of that and budget a few extra seconds. You cannot really just scribble all over the question as you could for a physical paper. Okay. Here we have a polynomial question. The polynomial has roots r1, r2, r3, r4. We have a new polynomial with roots r1 squared minus 1, r2 squared minus 1, r3 squared minus 1, and r4 squared minus 1. And we are asked to find q of 8. Intuitively speaking, it should be possible to transition over from one polynomial to another when you did something very nice to them, which this is fairly nice. So you wouldn't want to use Vietas here. If you use Vietas, you're going to get a humongous mess of trying to calculate the coefficients of Q. That would be very painful. It can be done, but certainly not worth the time in an AMC. If that's the only idea you have, you should really just skip the question first, because that will torpedo your chances of basically trying any other question in the remaining time. We're already up to almost an hour. So if let's say you want to calculate it without using Vietas, you want to solve it, and there's nothing else that's very clear, we can often just start with the definition. A monic polynomial means the highest degree, the x to the 4 term, is 1, and you've already given me 4 roots. So my q of z is just going to have these 4 very obvious factors. And those factors multiplied together exactly give you q of z. Now I'm a little lazy, and I think it is more economical here to just use a product notation. So I'm going to use the product notation for the rest of this. Now, I don't really see what to continue from here. But since the question just asks me for q of 8, I shall just substitute in z equals to 8. And 8 minus this is 9 minus ri squared, which, well, can be factorized. At this juncture, I hope you realize that this is already essentially done. Because we haven't used p of z at all, right? This is just working on the definition of q. We haven't used p of z at all, and p of z is precisely giving you this information. Because p of z, by definition, p of z is z minus ri, is the product of this. That is the definition of your polynomial. And so basically, the product of 3 minus ri is just p of 3. And the product of 3 plus ri would come when you sub in z equals to minus 3. You notice there will be 4 negatives which will disappear, so it's p of negative 3. Now, just do a very quick calculation, and if you do a very quick calculation, one of these is going to be 179, which is the option there, the other is 47. So your answer is 8,413. I mentioned earlier on about estimation. If you're sure you have this right, you can always just estimate it to be over 5,000, so it has to be the last option. Question 20. What's the value of this product? We know that this must somehow simplify in order to get any of our 5 options. And so if you must somehow simplify, that must come via a factorization. If this were to come from a factorization, the question is, there's no factorization for a sum of squares, right? So how do we actually factorize something like this? And there's only one identity which remotely looks like this, which is none other than your Sophie Germain identity. I know this question does look like some super old AIME question. That's where remotely the inspiration came from, and I only realized it after I had set the question. So Sophie-Germain identity is basically factorizing expressions of this form. And how you get the Sophie-Germain identity, the derivation, is sort of modified completing the square. You take a squared plus 2b squared, you square the whole thing. You minus 4a squared b squared. And that itself is also a square. So it factorizes as a difference of squares. The latter term is 2ab squared. So this is your factorization. Now once we have the factorization, we can ask ourselves, does that apply here? And the answer is yes, because 2 to the power of 10 is actually 4 times 4 to the power of 4. So what we have here is just x to the 4 plus 2 to the 10 can be written like this, and you just substitute in b equals to 4 plus 8x plus 32. I'm going to rewrite this in a way that will actually allow me to see the cancellation more clearly, and that's using one more instance of completing the square, but this time in the usual way. And hopefully you can see what's going to happen for our fraction, right? Your numbers are going to go up and down by 4, and by going up and down by 4, you're going to get, this is down by 4, and this is, sorry, what am I doing? I'm supposed to put squared plus 16, right? So my 5 becomes 1 squared plus 16, 9 squared plus 16. And the last one it gets to is 73 squared plus 16. For the other one, it starts off at 9. And it goes all the way until 1 further, which is 81. It's pretty easy to see that you get everything that's 1 more 8 in between, so everything cancels off except for the first and last one. And a very quick calculation tells us that it's equal to the first option, 17 over 6577. It's option 8. And we're into the final 5. Now the final 5 is sort of the domain of those of you who have a lot of experience in general. But don't assume that the final 5 questions are all going to be very hard, because every now and then an easy question sort of just sneaks in because the difficulty estimation has gone awry. So do try to at least give yourself some time to look at the later questions. You may find something that is surprisingly easy. Okay, oops, there we go. Question 21 is a counting question. 12 light bulbs numbered 1 to 12 are placed in a circle in that order. Initially, all the bulbs are off, and each bulb is equipped with a button, which when pressed, toggles the state of that bulb and its 2 neighbors. By pressing any sequence of buttons, how many possible states can be achieved? So toggle means on becomes off becomes on. But you can't just switch on and off a light bulb. In this very strange arrangement, you can only toggle 3 in a row at any time. So what we need to do is to figure out what exactly is the condition on the final state, because we can't really count it by sequences of moves because there are so many. Right? And we also know that some combinations of moves may lead to the same final outcome. So what I would like to say is that when you are doing this, you are looking for some kind of an invariance. An invariance literally means something that does not change. You are looking for some kind of invariance so that we know what is the collection of possible states at the end, and hopefully it will just be anything which satisfies the invariant. In order to have an invariant, you are looking for something which the move does not affect or does not mess up. And the move is pressing 3 in a row, but it could be any 3 in a row. So the only thing I can think of, if I want to have something that doesn't affect when I put 3 in a row, is to group them into kind of 3 columns. Right? The more mathematical way to say it would be modulo 3, but basically I just want to split it into 3 columns. Now I'm claiming, very unsurprisingly, that when I press any button, I am going to be toggling one bulb in each column. Now that means that I'm going to do the same thing to each column in a sense, but not exactly the same, because it could be some of them are going from off to on, some are going from on to off. So how do we do this? The way to do this is to realize that even though on and off, of course, are 2 different states, toggling does the same thing if we consider it in terms of parity, namely odd and evenness. So if we consider it in terms of parity, you are doing the same thing to all 3 groups at the same time mod 2, which is that each time you press a button, you are just adding 1 mod 2 to the number of bulbs that are switched on. In other words, you are changing the number of bulbs parity. And so therefore, the parity of the groups will always be equal. Now I'm going to leave it as a bit of an exercise for you to see why actually any such arrangement is fine. Right? The main idea is that you can always find a combination that switches 2 consecutive bulbs in the same group, let's say 1 and 4, without affecting the rest. So you can always get any such combination. And so therefore, all we need to do is find the number of odd configurations and even configurations in each group. Okay, and the number of odd configurations is just 4 choose 1 plus 4 choose 3, which is 8. The number of even configurations, you can take 16 minus 8 or just 4 choose 0, 2 and 4, which is also 8. And so therefore, if they're all odd, you get 8 cubed. If they're all even, you get 8 cubed. So there are 2 times 8 cubed, which is 1024 possible states. Okay, 22. So let A, B, C more than 1 be real numbers such that log A, log B, log C equals to 15 over 4. What is the smallest possible value of A to the log B squared plus B to the log C cubed plus C to the log A to the 5? Now this is ostensibly a log question, but it's not really about logs, because the question is not asking you to say what is the value. If it asks you what is the value, then it should just simplify. But it says what's the smallest possible value, so it shouldn't just simplify into the given information. We also notice that it says smallest possible, and the options look like as if, well, we're going to have some powers of 10. So the best possible way that we can deal with this, in order to make our inequalities a little bit more obvious to use, is to do a substitution to get rid of the logarithms first. So substitute x, y, and z for your logarithms, get rid of them, And of course, this means that your whole expression is going to become an exponential one. And also xyz is now the 15/4 from the question. Let's put it in. We get 10 to the power of x is for a, and log b squared is 2 log b, which is 2y. b is 10 to the y, log c cubed is 3z, and then c is 10 to the z, log a to the 5 is 5x. So this is going to be 10 to the 2xy plus 10 to the 3yz plus 10 to the 5zx. And we now need to find the minimum value of this. So we need to somehow get this to be related to xyz. And it makes sense that if you want to get them to be compared, you need to bring them together first, because each individual term does not involve z, and I don't really want to write it as something over x, something over y, and something over z. I don't think that helps too much. So what I'm going to do is to just fling everything into AMGM and say that this is greater than or equals to 3 times of the geometric mean. The geometric mean is the cube root of their product, which is just going to be 10 to the power of 1/3 of the sum of the exponents. Right? This is the geometric mean. And humorously enough, what we will do after this is to use AMGM again, because we have literally got 1/3 of this plus this plus this. So it is the most inviting possible case of using AMGM. So AMGM and then AMGM again is how we go about this. As we can see, this is going to now be xyz squared on the inside, and this can be computed. It's going to be b or c quite, a, b or c quite obviously, and I will just leave you to do the computation that shows you it is 3 times 10 to the 15/2. The answer is option C. Question 23. So S is a set of complex numbers such that the modulus of Z is 1 and the real part is positive. If 3 complex numbers are randomly chosen from S, what's the probability that their product is also in S? Whenever you have a question on complex numbers, you need to think of whether you're going to work on it in Cartesian form, meaning focus on the real and imaginary part, or in the polar exponential forms, which is focusing on the modulus and the argument. Here we have a bit of both in the condition, but the tiebreaker is that you're asked to deal with the probability that the product is an S, and products are more compatible with the polar or exponential form. So you would like to use that form, right? The polar exponential form, namely, you would much prefer the UVW is in S to focus on the modulus and the argument. And if you did that, you realize that this is actually going to be no problem at all, because it will be 1. So the product, the modulus of the product will already be 1. The only thing is the real part being positive. And the real part being positive actually corresponds to the argument being between minus pi over 2 and pi over 2. The argument of UVW is the sum of the arguments, and we know that we don't actually have any case where we can end up going full circle and reaching, let's say, 3 pi over 2 or something more than 3 pi over 2. We are bounded between minus 3 pi over 2 and positive 3 pi over 2, which means that the only way in which you're actually going to get your argument to be in this range is that the sum of the individual arguments is also in this range. And so this is a probability question where each of them are randomly picked from minus pi over 2 to pi over 2, and you want the chance that the sum is also in the interval. As before, there is no reason to use minus pi over 2 here everywhere. We're going to just scale it to a minus 1 to 1. So I will just use new variables so that we're not confused. A, B, C are randomly chosen from the interval minus 1, 1. And what's the probability that the sum is also in that interval? Minus 1 to 1. Okay, this is my new problem. And the answer to this new problem is actually quite a classic idea. Rather, the approach is quite a classic idea. When you're choosing from an interval of real numbers, right? Not a discrete interval where you just have got, let's say, 1, 2, 3, 4, or 5. You're choosing from a real value interval. The common way to think about this would be geometrically. So we can think of it as ABC is a random point Now I'm thinking of this as an ordered triple and not just as a set, because order matters. ABC is a random point in my cube. It's not the unit cube, although it is going to have the origin at the center. Right? In this cube, which has bottom corner -1, -1, -1, and the top corner here 1, 1, 1. So in this cube. And what's the chance that the A plus B plus C is in that interval is basically going to be what is squeezed between two planes. Now, A plus B plus C equals to -1, and A plus B plus C equals to 1, correspond to the planes x plus y plus z is -1 and 1, and those planes are going to be here and here. So these are your planes, and what you want is to get the volume of the space in between over the total volume. The total volume is 8. It's 2 cubed. It's not very easy to find that volume in between, but it's pretty easy to find the volume on the outside. Those are just pyramids again, right? Triangular base pyramids. So these have volume 1/3 times the base area, which is half times 2 squared, times the height, which is also 2. So this is equal to 4/3. So each of these pyramids has volume 4/3, and so your probability is 1 minus the probability of being inside these pyramids is 1 minus 2 times 4/3 over 8, which is 2/3 is the answer. Going a fair bit over time, and realize for the last couple of questions, it is going to take a bit more than 1.5 hours as I planned. But this is kind of normal, because in reality you're going to be writing a lot more messily, and explaining is going to take a bit more time than the actual thing. So it's conceivable to finish it in 1 hour 15 minutes if you are at the absolute optimum speed and efficiency for the whole paper. Okay, last two questions. Question 24. Let C be a function defined over non-negative integers as follows. C0 is 0, and for any n greater than or equals to 1, C of n is equal to Cn over 2 if n is even, and Cn minus 1 over 2 plus 2 to the log base 2 of n flawed if n is odd. I can go through a lot of things about, let's say, how we're going to try out a lot of small cases and experiments, and that will actually take a while to pay off. If you're doing the AMC and you're looking at some of these last few questions, sometimes you have to be a bit speculative because you don't really have time to approach this as if it were, let's say, a USAMO problem, where you can start from the simplest method and then after that proceed to the slightly more complicated method and then continue until you figure out the approach. For something like this, you have to be a bit speculative, and based on n over 2, n minus 1 over 2, and 2 to the log base 2 of n flawed, if we want to be a bit speculative, we can speculate that this has something to do with binary. I'm cheating, it does have something to do with binary, I said the question. But I did want to make it conceivable because there are lots of things here that signal binary. And if let's say that you wanted to understand what is going on here in binary, n over 2 and n minus 1 over 2 are basically just taking the last bit in binary and chopping it off. This would be the n over 2 or n minus 1 over 2, right? It's just chopping off the last bit if we are working in binary. Now, 2 to the log base 2 of n flawed is basically the largest power of 2, which is smaller than n itself. And that would actually be the first bit. So essentially, what does this function do? Now, what this function does is as follows. If the last bit is 1, then give me, alright, so I'm going to put a dot here to mean that we are currently applying the function to it. You put the dot, right? Okay, I'll put a vertical line over it. Right? So if we are asked to calculate this thing for the function and the last bit is 0, okay, let's start with 0 first. The last bit is 0, then we just drop it off. Okay, my arrow is clearly not pointing there in how I've drawn it. If your last bit is 1, you're still going to get rid of it. But in getting rid of it, you are going to be processing this and adding a 1 down here. Now, in a sense, we can also think of this here as if we were just putting a 0 in front, right? Because that's doing nothing. And you realize that this means that I've just taken the last binary digit, the last bit, put it at the front, and I'm going to continue processing the rest of it. So this operation is just nothing more than reversing it in binary. So reversing the binary representation is what we have done here. You see that? So reversing the binary representation is what we have done. And so if C of m equals to m, these are basically binary palindromes. Binary palindromes is what we need to count all the way up to 2022. It's a bit of bashing here, but it's not too bad, I can assure you, because it's binary, it's counting binary palindromes. That's very constraining. Right, so if we were to go through our cases, for 1 digit we have got 0 and 1 in binary. Right? For 2 digit, there is only going to be 11. For 3 digit, now the first and last one must always be 1 and 1, except for the 0, because you can't start with a 0. So you have got 0 or 1. So there's 2 possibilities. And for 4 digit, you still only have 0 or 1 in the middle. So this will continue you get 2, 2, then 4, 4, then 8, 8, because it depends on the number of digits in the middle, and you can only control half of them. So this is up to 10 digits. And I have got 11 digits to worry about as well. Now 2 to the power of 11 is 2048. So 2022 is 2 to the power of 11 minus 26, which is minus 32 plus 6. Right, so my 2022 is going to be, I'll just write down 11 ones. Is there 11 ones? No, this is 11 ones. And then I will adjust from that. The last bit should be, so minus 2 to the power of 5 means that you're going to have zeros. And then after that, plus 2 squared plus 2 to the 1. You didn't actually need to calculate this that carefully. My point here is just to see that this is actually very close to the all ones. So almost anything is going to be smaller than this, except for the case where you have got just all ones. That is not included because that's actually 2047. Right? But we include everything else. The next biggest one will be 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1. So that is already included in this count. Okay, so that is all that we have. We just need to count this total really carefully. And if we counted this total really carefully, you would find a total of 94. Just add it up. Okay, so last question. And the last question is at least my very Singaporean interpretation of the final questions for the AMC Geom. AMC Geom doesn't really involve that much cleverness per se. It usually involves a little bit more computation very many times. Okay, so this is offending a lot of people, but I think the general case is that the geometry questions, which are really nice, tend to involve a little bit more of like high-level properties, and high-level properties are not going to be the most prominent thing in many AMC questions and SMO questions and many short answer questions around the world. So here this is a very computational sort of question, but it is also a simple statement. It's just a right angle 3, 4, 5 triangle, and you want the smallest possible sum of the radii of these two circles which are drawn such that you have to be tangent to two of the sides and each other. So it's kind of like a pair of incircles in a way, yeah, in a sense, like a pair of incircles. Now, algebraically speaking, right, we have got 3, 4, 5. We need to be able to find something that relates together the radii of these two circles. I'm going to call them R1 and R2. Now I can see that, I can see that if I connect the two centers together, I do get R1 plus R2 immediately. I get it as in I get aligned with that length, not that I have actually found R1 plus R2 or its maximum or minimum. But what I can do is that, well, that means that I can get this length using a little bit of just Pythagoras. And if you simplify, you get 2 root R1 R2. So that's for this portion down here. Now, you also have the other two portions at this long remaining part of the hypotenuse. And what I can do to find those lengths is to use a little bit of trigonometry. Right. So if I just want to find out what is that angle over there, then one way that we can do it is to recognize that this is an angle bisector. Right. So this is an angle bisector. These are also R1. If I want to find out the value of my angle here, which is b over 2, I can just say that cosine b is equal to 3/5 and just transition over to my sine double angle or cosine double angle formula. So cosine squared b over 2 is 4/5, and that means that cosine b over 2 is 2 over root 5, and it's quite easy to get. Sine b over 2 is 1 over root 5, and tangent b over 2 is half. So if tangent b over 2 is half, that means that this length is 2r1. And we can proceed similarly for the other side as well. In the interest of time, I'm going to just say it's similar. We can get tangent of c over 2 is equal to 1/3, and so this would be 3r2. And that gives us an equation which we realize is kind of if and only if. So as long as my r1 and r2 are satisfying this equation, then there's only one way to draw a circle with r1 touching AB and BC. There's only one way to draw the circle radius R2 touching BC and CA. And the way that those two circles will also be tangent to each other is if the length in the middle is 2 square root R1 R2. So this configuration will work if and only if this is equal to 5. And I need to figure out what exactly is the maximum, sorry, I keep saying maximum, what's the minimum possible length of R1 plus R2? This can be done using calculus in some ways, but I'm going to use a little bit of just pure algebra. Right. What I would like to do is to use AMGM, and I'm not really sure how to use AMGM because I would like to use AMGM in order to remove the square root and to be able to say that this is less than or equal to something, a constant times R1 plus R2. Right? I would like to say that. In order to say that, I will need one more R1 than R2 in my use of AMGM. So I would like to say that this is less than or equal to, let's say, some P times R1. Maybe I should say P plus 1 times R1 and P times R2 for some constant. I would like to do that. And this would work, basically, I'll divide by 2. If this satisfies AMGM. So I need P plus 1 to be equal to, well, 1. So that the product of the two terms at the top is R1, R2. Now we can solve and we can see that this is actually going to be just like our golden ratio. We are going to get from the quadratic formula P equals to root 5 minus 1 over 2. And so therefore, right, once I have gotten this use of AMGM, I can put it back in and it tells me that 2r1 plus p plus 1. So 3 plus p is actually going to be my round here. And so r1 plus r2 is greater than or equals to 5 over 3 plus p, which we can just solve. Just evaluate. Okay, so I'll multiply by 2. And if you were to just simplify this, you are going to get 5 minus root 5 over 2, which is option B. Now, we know that definitely it is possible to have equality holding, right? Because equality holds as long as your R1 and R2 are in the correct ratio. And so you can kind of just adjust it until it's equal to 5. Now, interestingly enough, right, this actually just happens when omega 2 is actually the in circle. I have no idea at this point whether omega 2 is the in circle of holes in general, or if that's just a very nice coincidence for a 3, 4, 5 triangle. So I'm going to leave that to you as like one bonus little thing to think about. Yes, but that is all. Right? With that, we have covered all the 25 questions in about an hour 40 minutes, maybe hour 35, minus the introduction. So that's not too bad. And I'm sure that there are a few of you who could actually have done it way faster than me if you were doing it without explanation. Hope you found the questions fun. Do leave your comments below if you are just unclear of any of the things I've said, if I've made some serious silly mistake, or if you're just thought the paper was fun and want to say something nice. I would appreciate that as well. So all the best to everyone that's taking the AMC soon. And if I do get a chance, I may be recording the solutions for the actual AMC as well. But plenty of people are doing that as well. So if not, feel free to check out anyone else who goes over these AMC problems. So thanks again for watching. Please like and subscribe if you found this helpful, and hope to see you guys again soon. So bye for now.